Welcome everyone. Thank you all for joining this session with DSR, Decoding Scientific Research. I am Vasant and I will be moderating this session today. We are grateful to have with us today Mr. Vamsidharan Vemuri. He finished his bachelor's and master's of engineering in nanotechnology from Amity University, Noida. He also worked in JNCSR, Bengaluru for 2.5 years before starting his PhD at Lehigh University. His main area of research deals with using atomic layer deposition for developing materials with have application at low temperatures like low Kelvin. So a quick note before we begin, if the participants have any question, feel free to type it out in the chat session or wait till the end of the talk for your questions to be addressed. So on this basis, let's start today's session. Over to Mr. Vamsi.
Hi, everyone. Thank you for giving me this opportunity, especially Vasant and Decoding Scientific Research team. I just want to give a clarification. My work deals with low dielectric constant materials. Sorry for just writing low K. Low K is not low thermal, but it's low dielectric constant. And I thank everyone at DSR for giving me this opportunity today. Without any further delay, I'll be starting my talk. Today, I'll be talking about basics of atomic layer deposition from chemistry to its applications. I'll try to cover some topics. So hold on with me. Yeah, so atomic layer deposition is a very versatile technique. As you can see, that this is a periodic table given in a review paper recently. So as you can see, all these elements have been used to make materials. So when you look at the legend on the top, it says, as you can see here, it shows the element and it is coded with different colors. So these different colors represent the different types of materials that have been grown using atomic layer deposition. So when it is pure gray, it's just that the pure element has been grown, but when it's coded with different colors, so different materials, different varieties of these materials have been grown. So for example, if you see the different colors represent oxides, fluorides, nitrides, and chalcogenides in addition to the pure elements have been grown. So now you can see that these all materials have been grown by using atomic layer deposition from the start of its discovery to till now. We'll see why this is so versatile and how this has been developed and how this has been grown. Sorry. So atomic layer deposition and molecular layer deposition have two half cycles. They're complementary techniques. We'll see the difference between them. So these two half cycles represent one complete cycle, and when one complete cycle is done, one monolayer of film is grown. So these two half cycles are sequential and self-limiting. So we'll see what sequential and self-limiting are. So when you look at the atomic layer deposition, it has two half cycles. So each half cycle has a reaction going on. So when you look at the first half cycle, when a substrate with a hydroxyl termination OH group is introduced with a precursor for growing alumina here. So it's trimethyl alumina. When it's introduced into the chamber, the star here represents the surface species. So one methyl group and the hydrogen from the surface species of the OH get removed, and then the AlCH3 is bridged to alumina by chemisorption process. So once this half cycle is done, it has a precursor pulse and purge. Here, precursor pulse is when the trimethyl alumina is introduced into the chamber, and purge is when you use the carrier gas, which is nitrogen or argon in this case, to purge out the unreacted gases and reaction byproducts. So here, when you can see, the surface is hydroxyl terminated, right? So once the precursor is introduced into the chamber, all the surface reactive hydroxyl groups are, once the hydroxyl groups are full, then there is no place for the extra precursor molecule. So they just stay inside the chamber, and when you purge them out, they go out with the reaction byproducts. So that's why it's controlled. It's very precise. So in the next step, when you introduce next reactant in this case, which is water, so the same thing happens. So once the surface groups with aluminum with the surface aluminum groups with methyl functionalities on the top react with water, again it forms one more layer of aluminum and oxygen bonds with OH termination, and then the methane is byproduct. So this is two half cycles leading to one monolayer of growth. So the same thing is seen again in molecular layer deposition. So here the example material is alicone EG. Alicone is just a aluminum alkoxide. Alkoxide here represents that a alcohol is attached to the metal by oxygen bridging. So when you see here, the first step half cycle is the same. Only in the second half cycle, ethylene glycol has been introduced instead of water. So instead of aluminum and oxygen with hydroxyl termination, here you see aluminum with ethylene glycol termination. So here molecular fragments are introduced into the MLD. That's why it's called molecular layer deposition. That's the only difference between the two techniques. So with this, you can see that for every two half cycles, there is a monolayer growth. Since you can see only a monolayer growth, you can control this cycle number to get the precise thickness that you want. One important reason for using ALD or MLD is its conformality. So these films are really conformal. So as you can see in this figure, these are very high aspect ratio surfaces. High aspect ratio surfaces have very complex geometries. So when you see this picture, this was taken in 1990s, late 90s. So the conformality is very high, meaning the deposition is very uniform on the top and also in the trenches. But whereas if you look at any other deposition techniques, you will see that there is a shadowing effect. Shadowing effect means the thickness will be high on the top or low in the bottom, or because of these complex patterns, it might be having a shadowing effect. So that's the reason why ALE is important. And there is a temperature window for the growth. So usually the growth temperature is governed by this ALD window, which is seen in this picture. So if you keep the temperature too low, the growth per cycle, meaning the for every cycle would be very high because of condensation, or very low. The growth per cycle would be very low because of no reaction. Again, if you go too high, there could be a decomposition of precursors and there could be chemical vapor deposition kind of growth, meaning that it is not controlled like this anymore. It's not sequential and self-limiting. Or it could, the growth per cycle could be very low because of the desorption of the precursors from the substrate. So to keep the ideal ALD growth behavior, which is sequential and self-limiting, and to have precise thickness control, we need to have the temperature somewhere in between, as shown here. And the commonly used carrier gases are nitrogen and argon, which are inert. So we use research grade, which has very less oxygen in it compared to ultra high purity. And the pressure, it's not very high vacuum technique. It is pressure, it can be used in medium pressure ranges, which is in few tens of millitors. So there is a new technique that has been introduced to ALD community far later than the other techniques like chemical vapor deposition. It's called plasma enhanced ALD. It is better than thermal ALD. We'll see why. So when you see here, a plasma has been introduced while the ALD process is being going on. So plasma usually has electrons which ionize the gas that forms a plasma. Plasma has free radicals, electrons, ions, and sometimes the photons are emitted from the excited species. So the commonly used gases for making plasma are hydrogen, nitrogen, and oxygen. Sometimes the substrate that is shown here has been with this substrate is given a bias to accelerate the ions to manipulate the growth behavior of the plasma ALD. So the difference between thermal and plasma ALD is the first half cycle. During the first half cycle, It is very similar. It is during the second half cycle that you see that the plasma is the substrate is exposed to plasma. So when the plasma is given to the reactants while they're reacting, it does a few things. So as you can see here, the ion energy can be modified by changing the substrate. There are few things that can happen when a ion hits the substrate. It could be atom migration to sputtering. So as you can see, there are so many things going on: the film deposition, plasma chemistry, etching, and implantation. But atomic layer deposition has a very narrow range of ion energies. So if you have the ion energies in this range, that's when you see sequential and self-limiting growth. Whereas you can also remove some layers while doing the plasma chemistry. So why it is important than the normal thermal ALD? Because there are few chemistries which require very high growth temperature, which cannot be reached by using thermal ALD, but the same energy can be given by using plasma. So increased reactivity, and the temperature can be uh, the growth temperature can be lower than what you see in the thermal ALD, but the similar energy can be given to the substrate. The add atom mobility increases since the ions are impinging to the substrate with some energy. So what this does is it crystallizes the substrate at a lower temperature than what you see in normal thermal annealing cases. So if a material can be crystallized at 750 C, for example, you can see a crystallization behavior at very lower temperature than what you can see in the normal cases. So as I said earlier, the growth can be done at very low temperature, and the film properties are usually modified by varying the plasma conditions. Plasma conditions can be varied by changing the substrate bias. So the molecular layer deposition, as I said, has the organics incorporated. That's why it has more tunability, but we'll see why. Atomic layer deposition, usually it can be done from 33 degrees to 300 degrees C. These have been reported in the literature. As you can see here, the substrate is flexible. So it is a plastic substrate. If you are using plastic substrates for any applications, the deposition temperature should be low in order to not damage the surface or the chemistry of it. So when you look at the tunable properties of the alumina that is grown here at at 33 degrees to 175 degrees, in this case, the density starts to increase from 2.5 to 3 grams per centimeter cube. As you can see that the density and thickness is directly related to the growth temperature until certain case. The thickness starts to decrease from 120 to 170 degrees, but before that it starts to increase linearly. And all this happens because the hydroxyl incorporation inside the ALE films decreases as the growth temperature increases. So the hydroxyl content in the films is inversely related to the growth temperature. Whereas in MLD is a temperature sensitive technique. It could be done from 85 to 180. As you can see, at lower growth temperatures at 85 degrees centigrade, the growth per cycle, which is the growth that you see per every cycle, it is 4 angstroms per cycle at 85 degrees, and it keeps decreasing as the temperature increases. And also one difference between ALD and MLD is its density. Because the organics are incorporated into the films, the density decreases significantly compared to the pure atomic layer deposited films. So these organics incorporated into the film provides tunability to its properties, and the organics are inversely proportional to the growth temperature. So the amount of organics incorporated into the film substantially decreases as the growth temperature increases. So they have tunable properties. So when the organics are incorporated into the film, they can be removed later by subjecting the films to post deposition thermal processing. So this can be at a growth temperature or slightly higher for annealing, and then you can see that the density, refractive index, hardness, and the dielectric behavior of these films changes. So as we can see that till now we only spoke about the pros of the technique. As you all know that every technique also has some cons. We'll be discussing about the problems associated with the ALD and MLDs. So when you see at this deposition, when you look at this deposition, it is alicune as discussed earlier, but at lower growth temperatures, sometimes the precursors, like in this case trimethyl alumina, diffuse inside the film. This diffusion causes some non-idealities, which cause issues like double reactions. So what happens is when there is a uniform growth, this EG or ethylene glycol should be linear. But in this case, because of the non-idealities like precursor diffusion or sometimes higher temperature, these molecules have higher energy and they start to vibrate and they undergo double reactions. Double reactions meaning they bend instead of staying straight and take the active sites from the uh, next reactive site, which blocks from the precursors getting absorbed or chemisorbed onto the surface. This blocks the active sites and causes low growth per cycle than what we have assumed initially. So this causes submonolayer growth. Submonolayer growth means it's not a monolayer, it's islands. So there are some islands growing on the substrates, which is non-ideal. This is mostly seen in MLD, but sometimes this kind of behavior, precursor diffusion and islanding, is also seen in atomic layer deposition films. Also, MLD films undergo the structure collapse because, as you all know, that the difference between MLD and ALD is the organics, and if you remove them, they could form porous films, but also they densify and they cause reduction in thickness. This is good actually to make dense films, but if you want the films to be porous and you want them to have a stable structure, this is not recommended. So what you do is you deposit few MLD and ALD cycles. So when you do ALD after every few MLD cycles, that is just introduce water instead of ethylene glycol after every few cycles, you can see that you'll still get porous film because the majority is MLD and it has organics in it, but the thickness reduction decreases to 40 from 65. So there is 25% reduction in thickness. This is seen in literature. So what this is also by changing the heating rate. When you use faster heating rate, there is more decrease in thickness. That means there is more collapse. But when you use slower heating rate, there is less decrease in the collapse. And also when you see that you're using faster heating rate, the index of refraction, which is directly proportional to the density, decreases to 1.40, whereas when you're using slower heating rate, the decrease is higher, meaning there is more decrease in density. So nanolaminates and slower heating rates are recommended to decrease the structural collapse, which give you non-idealities. Now that you deposit your films and you are dealing with non-idealities, what you do next is characterize them. So one of the most commonly used characterization techniques for ALD community is quartz crystal microbalance and spectroscopic ellipsometry. We'll see what they are. So quartz crystal microbalance, as the name says, it is made of quartz crystal and it is microbalance. It can detect changes in nanograms. So how does it do that? So you can put this, as you can see in this figure, in your reactor where there is nitrogen flow. So while the growth is going on, so what happens is you have the quartz crystal directly inside the reactor with your samples. There is growth observed on the top of the QCM, and that's what you see here. So this is from 0 seconds to 1200 seconds. As the time progresses, you see a linear growth behavior. When one of this cycle is zoomed, you can see this. When a TMA is dosed, that is trimethyl alumina, which is aluminum precursor, is dosed inside that there is a substantial mass increase and it gets saturated. So that means that all the surface active sites have been taken and then it is saturated. And once you're purging it for some time, which is 6 seconds here, and then you again pulse or dose water inside your reactor, there is a slight mass gain, and then there is a decrease. It means that initially there is some mass gain, but after that there is also mass loss because some of the methane groups are removed. So this is the zoomed in version of the each cycle. So what you can see is you can see the change in mass and thickness. The change in mass is seen by the change in frequency. So every crystal has a resonant frequency to it. In this case, it could be somewhere near to 5 megahertz. So when you see some mass depositing on the top of the crystal, what happens is the natural resonant frequency dampens, and that change in the frequency can be calculated by using this formula. And also you can calculate the change in thickness. So this is a simple equation that you need to plug in. So you just need to know the density of the film and change in mass, which you get from the previous change in frequency equation. So next is spectroscopic ellipsometry. So one obvious benefit for using QCM is it can be used in situ. In situ meaning you can use this technique while the growth is going on. So you'll know how the growth looks like, if it's ideal ALD or non-ideal ALD. So for ideal ALD, it should look like this, which is linear. But for non-ideal ALD, it wouldn't look linear. It would look something like linear, and then it gets saturated at some point. It's non-ideal ALD, meaning that there is something wrong going on. So the other technique is spectroscopic ellipsometry. So here, it can be used both in situ and ex situ. So while you're doing it in situ, you can calculate the both index of refraction, which talks about the density of the material, how the light interacts when it passes through different densities, and extinction coefficient. Extinction coefficient refers to the absorption of the wavelength of light. So some wavelengths of light could be absorbed depending upon the chemical composition of the sample, so that can be observed. So what you usually get is a thickness map of the whole sample. So if you use a big sample, you can write a program and then it stitches. So it collects thickness at various points and then gives you a heat map or color map shown like this. So you can see how uniform the growth is and thickness is. So due to inconsistencies or some irregularities in the flow, you can get non-uniformities as shown here. And then from this, you once you get the data, you fit it with the Cauchy equation if it's a semiconductor. So anytime before you do ALD, you know what material you're going to deposit and you know what is the composition of it approximately. So what you do is you have a Cauchy equation for every material which is known. If the material is not known, it's a different case. But if it's known, you have a Cauchy equation and you fit to it. That's how you get the thickness and refractive index. And one more benefit of this is you can get optical conductivity and optical resistivity, which could be useful for semiconductors and nitride semiconductors by changing the deposition parameters. So without doing any electrical measurements, you can directly get the optical resistivity and conductivity by using this equation, by using this technique, sorry. So one more majorly used technique is X-ray reflectivity. So X-ray reflectivity or X-ray reflectivity stands for XRR or X-ray reflectivity, sorry. As the name suggests, the basic principle is reflection. So as you see, up until certain theta, it is specularly reflected. Specularly reflected meaning it's like a mirror surface. All the reflections are, all the X-rays are reflected from the surface. They don't go inside. It is called specular reflection. But once you change the theta to a certain angle, that's when the X-rays start to enter or penetrate inside the material. As you can see here, from 0 to 1.5, it is critical angle. So critical angle is the angle where the X-rays start to penetrate inside the material. So the data, typical X-ray reflectivity data looks like this. So by looking at the critical angle, that means the angle at which the X-rays are penetrating inside the material. It gives valuable information about the density. By looking at the oscillations, you get the thickness of the film. And by looking at the amplitude, meaning how big the waves are, or these fringes are, you can get the contrast in density. And also you can get the decay rate. So you can get the thickness, sorry, the interface roughness or the surface roughness. So there could be many roughnesses, right? So this could be your substrate, and then you could put two films on it. And if you put two films, there are two interfaces. So those two interfaces might not be smooth; they might be rough. And the topmost surface also has some roughness associated to it. So by looking at the decay of these oscillations, you can get valuable information about the surface roughness. So you can also get electron density by looking at the data. So usually while you buy the X-ray equipment, the X-ray diffractometer, they give you the software for doing the X-ray reflectivity analysis on your data. But if you are sending the sample somewhere and you want to play with the data yourself, the commonly used openware softwares that are available freely are Genex and Reflex. GenX is Python-based program where you need to code to fit your data, but whereas Reflex is a normal fitting program. It can be used for both Windows and Linux. So this is very valuable tool. You can use it both in situ and ex situ. In situ meaning throw a sample and then see how the density varies by doing temperature dependent measurements. So usually the only thing that happens is you have a stage which can go from room temperature to approximately 1000 degrees C. So at 50-degree centigrade intervals, for every 50-degree intervals, you can see how the density varies. So by changing the temperature, you can look how your film varies. That's why this is a very critical technique for thin film researchers. One more valuable technique that we use is in situ and ex situ Fourier transform infrared spectroscopy. So usually the in situ FTR is really important. It's not that ex situ FTR is not important, but by using the in situ FTR spectrometer, you can actually get the reaction mechanism. So if you look at this, this material is tin cone. Tin cone here is a molecular layer deposited film. So it has tin and organics inside it. The organics come here from butanediol instead of ethylene glycol. Sometimes other organics like ethylene glycol can also be used. So for every step, you can see the changes in the film chemistry and sometimes the intensity growing. So when you put 15 cycles, you just have 15 monolayers of the film, which could be 1.5 nanometers to 2 nanometers, depending on the growth per cycle. So you can see the slight changes in the thickness, and the chemistry can be predicted or can be accurately seen by using FTR. The only problem is you cannot be quantitative by doing FTR, even though some people do quantitative analysis by doing some more mathematical calculations on the data. But usually this is very qualitative. So every half cycle, you can see the changes. So you can deduce the reaction mechanism by looking at this. Other commonly used surface techniques are X-ray photoelectron spectroscopy and ion scattering. As most of people know, XPS is a very common characterization tool that's used by researchers across various domains. This is also useful for thin film community, not only ALD. So as you can see, when X-ray photon comes and hits the sample, it knocks off electrons from the shells, and that difference in the so that kinetic energy and the difference in the binding energy can be calculated by this equation. So what you can get is quantitative uh, chemical composition by using X-ray photoelectron spectroscopy. So you just get the data and you fit it using Excel or any normal data analysis software that researchers use, and then you get valuable information about the chemical composition, the nearest neighbor, the oxidation state. So this is very valuable in predicting the composition of the films quantitatively, unlike FTR. The other, sorry, the excuse me. The other commonly used techniques are ion scattering. So here there are three types of ion scatterings. When you look at the three types, there are low energy ion scattering, Rutherford backscattering, which is also called as high energy ion scattering. So what ion scattering means here is when the ions are accelerated and implanted onto the surface of a sample. Scattering, elastic and inelastic. Mostly low energy scattering and high energy scattering, like Rutherford backscattered samples techniques, use low energy and high energy ions, but they use ions which are non-reactive. So if you see, LICE is a low energy scattering. It uses helium, nitrogen, and argon. The accelerating voltage is 500 electron volts to 20 kilo electron volts, whereas RBS, it uses helium 2 plus ions. The accelerating voltages are very high. The order of magnitude is higher than what you see in LICE and SIMS. So as I said earlier, LICE and RBS, they just use inert ions, which does not change the chemistry. So you implant these ions onto the surface of the sample, they knock some atoms off, or they change their kinetic energy, and that kinetic energy is seen by the detector and you can know the chemical composition. But whereas in SIMS, you use reactive ions. SIMS stands for secondary ion mass spectroscopy. So as you can see, the name itself suggests secondary ion. So what happens is when you implant these ions onto the surface of a sample, these ions knock some of the atoms or ions on the top of the substrate or the sample that you're looking at, and then that secondary ion mass is seen by a mass spectrometer. So as I said earlier, low energy ion scattering and Rutherford backscattering uses uh, inert ions, so it doesn't do any chemical reactions. But whereas cesium and oxygen ions are, as you know, they're very reactive. They react with the surface atoms sometimes, and they get implanted into the sample. Even though they say it's a non-destructive technique, this sometimes could be a destructive technique because it could change the composition. Even though it reacts with the atoms sometimes in the film, and sometimes it reacts and then again comes out, you can distinguish between the atoms and the ions which are reacted with cesium or oxygen. And then you can get it because you use a mass spectrometer. You would know what would be the mass of the ions if they react with cesium and oxygen. There are some more techniques which are used to measure the porosity. These are called porosimetry techniques. So ellipsometric porosimetry is a very commonly used technique for thin film community. So usually what you do is you put your sample in a vacuum kind of environment, and you put some kind of reactive vapors inside, and you increase the pressure until the film or the porous material here gets saturated with these reactive vapors. And again, you desorb these vapors. And while you do this adsorption and desorption process, you would be having a light always incident on your sample by using ellipsometry technique. So what you do is, while you're having this absorption and desorption, you're looking at the changes in thickness, refractive index, and density of the material. So you know what changes are going on, and you fit the data later on to get the porosity information. One major drawback is it cannot measure the closed pores inside a film. It can measure only open pores. It is very obvious because once you're using these reactive vapors, they cannot diffuse inside if the material is closed. They can only go to the pores which are open. That's a major drawback. That's why people go to a complicated technique which is called positron inhalation. So usually when a radioactive beta decay of 2211 sodium isotope happens, it gives out a positron and a gamma ray that shows the start of the reaction. These are usually uh, these reactive sources are usually found in lab scale spectrophotometers as well. So when you inject a positron inside the material, it forms positron and electron pair, which is called as positronium, which is also represented by PS. So these can be formed into two types, which is called para and ortho based on the spin. So if they have opposite spins, meaning if the positron, which is an antimatter of electron, has a up spin, and if the electron with which it recombines inside the material has down spin, it's called para. So this kind of recombination of electron and positron, when a when any antimatter and its complementary matter recombine, they annihilate into energy. So that annihilation lifetime for parapositron is fixed here. So when this parapositronium annihilates, it gives two gamma rays, and the lifetime is fixed. It's 0.125 nanoseconds. Whereas in case of orthopositronium, it is very stable. So orthopositronium is when an electron and positron of similar spin recombine, and they still are very stable, and they are looking for another electron which is of opposite spin. So if the orthopositron does not recombine with any opposite spin electrons, it annihilates into 3 gamma photons, and the lifetime is 142 nanoseconds. But if it manages to find an electron of opposite spin, it depends. The lifetime decreases from 142 to 1 nanosecond. So if this orthopositron finds a electron in 1 nanosecond, it recombines and annihilates into 2 gamma rays. This process is called as orthopositronium. And by looking at the orthopositronium lifetime, you can reduce the pore size. And since this is used to reduce the pore size, the orthopositronium lifetime is important. So the pick-off process, the process where it annihilates into 2 gamma photons, that's important. So we use some use some electrical measurements to calculate the dielectric constant and leakage current. So the commonly used methods are capacitance and voltage to calculate the dielectric constant. Here you have a substrate as shown in this figure. You use two probes. One is the top, one is attached to the top, and one is attached to the bottom. So if your sample is alumina, for example, and you want to measure the dielectric constant, you have a top metal on the top deposited later to form MIS devices, which stands for metal, insulator, and semiconductor devices. So since alumina is a dielectric, you want to measure the dielectric constant, you do CV measurements on it, capacitance voltage. So what happens here is when you apply a certain voltage and cycle it from negative to positive, the like charges repel and the negative or the oppositely charged particles start to accumulate near the metal surface. As you switch the voltage, the opposite happens. That's why you see the curve flipping from, this is called accumulation at the top, and this process is called as uh, inversion process, and this is called as inversion capacitance. So you can measure this by using the parallel plate capacitor equation. So the capacitance is usually given by this parallel plate capacitor equation. The D is nothing but the thickness of your sample, and K is the dielectric constant that you need to calculate, and A is the area of the metal pad or contact that you're using here. And the other technique that you use is current voltage, or it's called JV, or current voltage, current density versus electric field. So what you can do is you can calculate the leakage current here. So by applying the current and voltage, or by applying the voltage, and you go from 0 to 100 or any value, negative to positive, you can see how the current changes. So if there is a sudden increase in the current at certain voltage, you can say that that is leakage current. So usually this is plotted as current density and electric field. So when you look at current density is amperes per centimeter square, the centimeter square comes from the area of the metal pad that you're using, and the electric field is calculated by using the thickness of the dielectric that you're going to measure. Next, I'll be talking about the applications. So ALD is applied in various fields. These days, it's used in displays for barriers. So as you can see, this is a very flexible substrate. As I showed earlier, ALD can be done on flexible substrates because it can be also done at lower temperatures. So at lower temperatures, the alumina deposition is done. Alumina is a very good barrier. So these thin films get bad with time because of the moisture diffusion, and alumina is a good moisture repellent, or it could be used as a hermetic seal while maintaining the mechanical flexibility. It's also used in fuel cells for making catalysts. It can also be used in catalysis these days. It is used for making carrier selective contacts in silicon-based heterojunction solar cells. So carrier selective contacts here, meaning they separate the charges and doesn't let them recombine faster. So there are two types of contacts, electron sensitive and hole sensitive. So by using these contacts, you can have the efficiency higher. By using these carrier selective contacts, the efficiency can be increased. And also it is majorly used in microelectronics. So as I said, I'll be talking about few applications. So I'm focusing majorly on the microelectronics part here. So as you see, this is a basic IC diagram. IC here is integrated circuits, which are commonly seen in the computer chips. So it has two components, front end of the line and back end of the line. So in front end of the line, you have basically transistors, and in the back end of the line, you have interconnects connecting these transistors. So the transistors, as you see here, have metal contacts, and they are connected by these copper interconnects here. And as you see, this is a cross-sectional view. And as you see, every year, the number of components that are used on these ICs double. This is Moore's law. Gordon Moore was the first person who predicted that this would happen. And starting from 2002, you see that the number of components that are packed onto the chips increases exponentially. And this process is called as scaling. Scaling, even though started to increase the efficiency and the working processing power of the ICs, it started to show some resistance and capacitance delays. So these new materials and these materials that are used for ICs can be grown using atomic layer deposition to handle those problems. And one benefit of using ALD is again its conformality. So as you can see that these parts look really complicated and they have very high aspect ratio surfaces. And the only deposition technique that can offer very high conformality is atomic layer deposition. That's why we use this. So as you can see that it has multiple components in both transistors and interconnects. In transistors, there is a gate which uses a metal, sorry, it uses a oxide, metal oxide, yeah, and it should be insulating. And as I said, because of scaling, they become very thin and thin. The leakage current starts to increase. So you use high dielectric constant materials for that. So as you can see, the commonly used the metal gate or the dielectric inside the gate oxide. The gate oxide is silicon, but recently it's been replaced with hafnium and alumina, hafnium oxide and alumina. And if you look at the interconnects, you can see that there is tantalum nitride, silicon carbide, and silicon oxide. So this gray material is silicon oxide. The dark gray material here, the liners, it's silicon carbide, and the material that you see here, this is copper, but the adjacent lining material used is tantalum nitride. So every material used in all of the microelectronics can be deposited by either thermal ALD or plasma ALD. And the recent advancements, and I would like to conclude, and then by talking about the recent advancements, recently they showed that there could be area selective atomic layer deposition done. So initially what they used to do was they used to pattern a sample, they grow a sample and they use a resist and then etch away the rest of the sample by using plasma or sometimes liquid acids. So this is called top-down approach. So usually by using this top-down approach, they design microelectronics, but this sometimes is harmful because this resist poisons your film, and also the etching process can uh, give you some defects which are not good for electronic applications. Recently, however, they started to grow area selective ALD films by using chemistry. So they coat this green parts with some functionalities and the blue parts with some other functionalities, which lets the ALD process occur only on the blue part and not on the green part. So you can see that the selectivity on the blue part is high and the growth process is linear. As I said earlier, if the process is linear, the growth is linear, it is ideal ALD process. But if you see that as the number of cycles are increasing and the process starts to go like this, like it's non-linear growth, right? So this is non-ideal growth and this is not ideal for ALD. So you can clearly see that for certain number of cycles, the growth is blocked on the green part. So this is how they developed area selective ALD. It is good for microelectronic devices because this is not top down. You're not etching anything. You're growing something from the bottom up. You're adding layers to it and there is no scope of defects or contaminants in it. So this is pure material. The other new technique that was introduced very recently is solution ALD. So it was given by German group in 2015. What they do is they use peristaltic pumps and they introduce precursors sequentially into a microfluidic chamber. So by doing this, room temperature deposition is also possible. And sometimes when the precursors are less volatile, meaning the vapor pressure of the precursors is low, even at higher temperatures, they can mix those precursors sometimes in non-reactive solvents and do solution ALD, and they can get the atomic layer deposition. So with this, I want to conclude my talk and say thank you, and I'm ready to take questions.
Thank you, Mr. Vamsi. It was a wonderful talk.
Thanks, Vasan.
The participants can. Thank you, Vamsi. The participants can either use the chat box or activate your microphone to interact with our speaker.
Hello, sir.
Hey.
Sir, my name is Mohammad Shanu. I'm a first year PhD student at Department of Physics, IIT Delhi.
Okay.
Sir, in the slide deposition issues, you said that the molecule start bending. So how you came to know and how you find out by which technique you get that your molecule is bending?
That's a good question, Shanu. So if I go back to that slide, that's non-idealities, right? That's here. So when you predict a ALD cycle, you know the mechanism and you know the growth temperature. But by changing the growth temperature, sometimes you give more energy to the sample. So the linear chains that are supposed to be linear here, so the organic molecules that are supposed to be linear here sometimes bend. Your question is, how do you know that they are bending,
Yeah.
right? We don't know that they are bending. So what we know is that it is not ideal. There is no monolayer coverage. So to know if your sample is deposited uniformly on the substrate, you do many kinds of characterizations. One could be using the ion scattering techniques. You can raster scan. Raster scanning meaning if you have a rectangular sample or square sample, you start at origin 0 and you go from 0 to 1 in X and Y directions. That's how you raster scan, and you know the chemical composition at each spot. Sometimes you deposit thin films and see at spot 0 you have the chemical composition that you're expecting for aluminum and oxygen and carbon. That means that you have sample. And some places you have bal spots. Bal spots meaning you're hitting directly the substrate. You get silicon and oxide. That's how you know that it is not monolayer, and that's how you know that it's not uniform. And how do I know that if the molecules are bending? You cannot do any characterization for that, but you can do some density functional theories, calculations to see what happens. So sometimes that is a possibility, and that's what happens. So this is called double reactions, and this is very commonly seen in molecular layer deposition.
Okay, sir. Thank you, sir. So my another question is that you said that we use this technique in microelectronics. So
Yeah.
now they suppose that these processors like Intel 7 nanometer and Apple A14 bionic chip, they I think go to 7 nanometer. Now they are going to 5 nanometer. So how they make? I mean, what technique they use to go such a nano region to make these processors?
So it is not one technique. It uses multiple techniques to make a processor, right? So it uses lithography to make the patterns. Let me go to that slide. So they first start with a silicon wafer, and then they use lithographic techniques to pattern the transistors on the top. And then once the transistors are fabricated, they send this to a different group where they do interconnects growth. So when you ask me how do they do it, they use so many processes. So every time they go from 7 to 14 to 7, 7 to 5 by changing the size of the uh, smallest components that are being used. So they have to undergo a vast change in the lithography and other processing techniques to get there. But as I said, ALD is very conformal technique. So even if you go to 2 nanometers, atomic layer deposition can be used. But the problem is not with the atomic layer deposition, but the problem comes with other lithography and etching techniques. That's why they are coming up with bottom-up approach. As I said, area selective ALD could be revolutionary for these people. It's still in infancy, but yeah, it can be used in the future.
Thank you, sir, for having this nice talk. Sir.
Thank you. Any other
Uh,
questions?
Vamsi, I've got a small curious question. Will it be possible to produce liquid crystals based on this ALDs? Because you said like there are organic moieties which can be functionalized. So is there any possibilities, or it is being used
So,
to make liquid crystals?
so I have no idea about liquid crystals, Vasant. Can you
Okay.
explain what liquid crystals are, and then I might think and let you know.
Okay. These liquid crystals are those substances which have these organic moieties which dangle so that it behaves as a liquid, and there are some fixed spot so that it is oriented in a specific direction. So it becomes like an crystal, but it has a moving part and organic moiety, so it behaves as a liquid also. So those we use it in liquid crystal displays, and now these liquid crystal displays are being gradually replaced by OLEDs. So I was just curious to know if you have some idea on it.
Okay. No, Vasant, sorry, I don't know. I didn't see any literature citing it has been used for growing liquid crystals, but I could be wrong. Don't call me on that. I
Oh,
don't know that.
okay. Thank you. So do we have any other question? Vamshi, I have got two more questions.
Yeah.
One is this deposition like ALD as well as molecular layering, is it always multi-layer or do we have monolayer also being used in the applications?
That is a good question, Vasan. So we never use monolayer because, as I said, monolayer sometimes could lead to islanding problems. So we use multi-layer. Multi-layer meaning we do at least 2 or 3 cycles to make sure that the surface is covered.
Okay.
So initial reaction mechanism would be different. So when you have a silicon substrate with hydroxyl termination, it could not be hydroxyls everywhere because no matter how much you functionalize, there is some water adsorbed onto the surface. Sometimes there is adventitious carbon, which would be blocking the active sites. So what usually happens is no matter how much you clean and put it in the reactor, there is some time lag. And that time lag is enough to give some adventitious carbon and water adsorption. So what it does is it blocks the active site. So it won't be monolayer in the first uh, layer that you put. But if you put like 2 or 3 cycles, it will be covered completely. That's why.
Oh, okay. It is good. I've got one more like how do we control the inertness of the surface molecules because we know because it is in the atomic layer or the molecular layer, these
Mhm.
molecules tend to be more reactive when it comes to the room temperature or the atmospheric pressure because we have a lot of presence of moisture on all those. So how do they stabilize this and what makes them stable?
So that is a good question. Some molecular layer films are not stable in atmosphere. That's why you do MLD and ALD. So the thing is, uh, moisture has the atmosphere has moisture and oxygen. Both of them are very intrusive and they tend to oxidize the materials. But with ALD, what happens is you mostly put nitrites, fluorides, or oxides. These films are inherently very inert. So no matter if you throw them down, like accidentally, if you drop a sample down, you can just clean it and it will still be fine. It will be pristine. But if you have a MLD film and if you put it outside for a day, its chemistry changes. So you can do an FTIR as soon as the deposition is done versus FTIR after a few days. The chemistry changes. The water goes in and it oxidizes the chemical moieties. Yeah, the chemistry changes. It's not very stable. But ALD films are stable, but not MLD films. That's a good question.
Okay, thank you. So with this connection with this, I've got one more question, the last question.
Yeah, awesome.
What is the practical? Can you give us an example of few examples of ALD which is practically used and MLD which is practically used?
So atomic layer deposition is practically used for barrier layers right now. It is in commercial
Batteries
scale.
or
No, it can be used in any barrier layer application. So it, as you said, batteries. It can be used as a barrier layer for lithium electrodes. It can be used as a barrier layer in thin films where the water and oxygen cannot permeate. It is
okay,
also used in semiconductor industries by Applied Materials and Intel to deposit the gate oxides, as I said, high dielectric constant materials for
okay,
the transistors here. And
okay,
MLD, I don't really know what the applications are for MLD, but it is, I think, still in infant stage, but I could be wrong.
okay,
So people are still trying different things using MLD, but I don't think it is commercial yet.
okay. I think we'll. My question is over.
Yeah, so I have a question. This is Kiran here.
Yeah, hi Siri.
So Vamsi, so I wanted to ask you one thing. So this kind of films that you're growing, what kind of crystallinity do you get? Is it an amorphous film or a crystalline film that you're trying to form on these
So that's a
transistors?
good question. As I said earlier, by using thermal ALD and molecular layer deposition, you always get amorphous films because the deposition temperature is limited to 300 degrees C. And as I showed earlier, to get ideal ALD behavior, you cannot cross. You guys can see my screen, right?
Yes, yes.
Yeah, so you cannot cross this temperature window. So if you go too high, what happens is you decompose the precursors that are deposited, or sometimes you dissolve. So you get only amorphous by using thermal ALD. But in case of plasma ALD, since the ions impinge and give some extra energy to the substrate, you can get polycrystalline and in some cases crystalline films as well.
Okay. And one more thing that I wanted to ask is, so what kind of techniques you can use to find out where the elements are exactly sitting on your substrate?
I didn't get your question, so
What kind of methods you can use to quantify or measure, like for example, where your atoms are sitting where? So now you told that maybe you can use some kind of the gentleman in the first one who asked a question, he was asking about that instead of being a linear bond, if it is a bent bond.
so
Told
the
that you
thing
can
is,
take, yeah.
the thing is you cannot say which atoms are sitting where, but you can see where the atoms are not there. So it's supposed to be an ideal technique, and you do everything right. You put a hydroxyl termination on the surface, and then you start your growth. So it's supposed to be a very uniform technique. But sometimes, as I said, there could be adventitious carbon and some dust particles that can sit on the surface and not give uniformity. So it is very tough to know where the atoms are and where the atoms are not there. But you can do ion scattering techniques. So, for example, if you look at the let me just go to the slide. So if you use low energy ion scattering, you can get a depth resolution of few nanometers, like 1 to 3 nanometers or something. So you can put down a very thin film and see where the atoms are, and the chemical composition is at that local spot by raster scanning, and then you can get a complete depth profile of the surface. But it's still not conclusive enough to say where the elements are and where the elements are not there. But it will give you a very rough idea. If you
Yeah,
want to see the, sorry,
yeah,
go
I
on.
think so. You can give a very rough idea. But
Yeah.
what I wanted to say is, like, say, if you're growing, say, a monolayer or a monolayer and a bilayer entities, I don't think so. These methods can be used to check whether there are pinholes or not. Why?
No, no,
Because this is
this is very useful for monolayers actually. The lice
this
is
is
very useful. Yeah, it is very useful to see the islanding and techniques like that. So if there is any growth inconsistencies, these ion scattering techniques are useful to see that. But you cannot tell uh, where the atoms are and where the atoms are not there very conclusively. But you can say the islanding or the uniform growth by using these techniques, especially for monolayers.
okay. Since you mentioned the word nanometer, so I was thinking that for monolayers and all, it may not be possible.
Oh, no, no. Depth resolution up to few nanometers, but in angstrom scales, this is really good because you use ions, right?
Okay. Yeah, that's all from my side, Vamsi.
Okay. Are there any other questions?
I think like there are no further questions. So do we have to wait, or we'll wait for a minute? If someone has got a question, we will answer them.
Sure. Sure.
If not, we'll. So in case of no further question, on behalf of all of us, I thank Mr. Vamsi for accepting our invitation. Thank you, Mr. Vamsi.
Thanks,
And then
Vasant.
thank you, Vamsi.
Thank you. Thank you for giving me this opportunity, guys. Yeah.
And it was a wonderful talk on atomic layer deposition. And if someone wants to pursue what they are doing some work on atomic layering, this will be a perfect presentation for them to understand what kind of characterization technique they can be used and how to understand the atomic layer which they have prepared. So thank you. Before we end, there is a small notification. There will be an active link in the chat box for the feedback form. So kindly let us fill it up so that we will know about our drawbacks and goodnesses. Thank you all for joining this session. And this lecture will be also uploaded in our YouTube channel called Decoding Scientific Research. So we'll give this link also shortly. So thank you everyone for participating. Thank you all once again.
Thank you, Vasant, and thank you everyone for asking wonderful
Thank
questions.
Thank
thank
you.
you.